In the previous session, we have considered comparison of paired population means, that is comparison between population means from two distributions. The distributions are multivariate normal distributions. In this discussion, we are going to generalize this to the case when we have more than two populations. We assume that we have k, a finite number of populations, each of them multivariate normal, and we are interested in testing the equality of the k population means. Obviously, we can handle this by repeated paired comparison tests, but if we can handle the whole thing in one go, it is obviously more preferable. So, what we have is essentially we have now k populations, so that we have the first one, say population 1, the first population with sample size n1, and the observations are the random sample that we have. These are being denoted by x11 to x1 n1. Note that we have two subscripts now. The first one, as you can see, pertains to the first population, that is why it is 1 throughout, and then the second subscript is for the number of observations within that population. So, we have this random sample x11 to x1 n1, each from the normal, the multivariate normal, p-variate normal mu1 dispersion matrix sigma. Similarly, this setup is repeated to the kth situation, where we have population k, the kth population, sample size is n k, it's not m, n k, and the random sample is now k 1 to k n k, and we have them coming from the p-variate multivariate normal with mean mu k and sigma. Note that to differentiate between the populations, we have different notations for the means. The ith mean mu I is pertaining to the ith population, which has sample size ni, but we have to take care of the fact that the covariance matrix is same throughout. It is the same sigma, and we have only the usual assumption that sigma is positive definite, which we are denoting by this sigma greater than 0. So, the null hypothesis we are interested in testing is H naught. The null hypothesis is mu 1 is equal to up to mu k. So, essentially the problem is testing for equality of k population means. Obviously, when the populations are multivariate normal, the k populations, the ith population is multivariate normal p dimension with mu I, mean and variance matrix is, covariance matrix is sigma. So, this is being tested, the null hypothesis is being tested against the alternative that H naught is not true, which is nothing but there exists at least one inequality. So, the equality relationship is violated at least once, that would violate the null hypothesis, that all the means are equal. Okay. So, we apply the usual, we apply the likelihood ratio test principle for testing this null against this alternative. And if you recall the likelihood ratio test principle, it is centered around that likelihood ratio, which we denote by a lambda. So, we denote the likelihood ratio is lambda, and just recall the definition. We have the numerator is the supremum over the likelihood function. Now, this is written as a function of the, we are considering the parameters here. So, we denote all the parameters that are coming into the picture. So, they are k such means mu 1 to mu k, and obviously the dispersion matrix sigma this supremum is being considered over the parameter space under the null hypothesis, that is the restricted parameter space. Hence, we have this theta, capital theta with a subscript 0 here. Okay. Just like for the hypothesis we have h with a subscript 0, this is the same thing. So, this supremum is being considered over the parameter space under the null hypothesis, and this is over supremum of the likelihood function mu1, mu2 to mu k and sigma, and this supremum is over the unrestricted parameter space. If you want, you can also include the observations here. So, we may as well write the observations which are x11 to x1n1, and then for the kth one which is xk1 to xknk. So, we extend this. Similarly, we have the observations for the first population and similarly for the kth population. So, let us again go back to this parameter spaces, this notation that we have used. The first one is, so let us specifically just describe this for once. So, what we have is theta naught is the parameter space of mu1 to mu k, such that basically the null hypothesis is all the population means are equal. This is equal to say some common mu, and they are belonging to Rp obviously, because we have the p-variate multivariate normal distribution and we have the variance covariance matrix, a positive definite one. So, this is the parameter space under restriction, restricted by the null hypothesis, which we are going to consider in the numerator of the likelihood ratio test principle, and the unrestricted parameter space as well. It is just rewriting the parameter space, because we do not have any assumptions here, and we have its mu1. We have not mentioned the sigma here. So, obviously, we have to do this. Let us erase a bracket over here, and then we have the sigma such that we have mu1, no question of equality here. We have each of these mu1 to mu k each distinct belonging to Rp, and we have the positive definite variance covariance matrix. Next in question is the likelihood function. Recall the likelihood function that you have considered exactly in the situation where you had sampling distribution of where you had considered multivariate normal distribution and sampling distribution from the multivariate normal distribution. When you had a single population, we handled the situation in a way like the population size was n, the sample size was n, the dimension was p, and we knew how to handle, how to write the likelihood function. Now, exactly the same thing will be done here. The difference is that you have, for the ith you have k populations, that is the first difference. The ith population has sample size ni, it has the mean vector mu I, and since the populations are all independent, we just consider the likelihood function for the ith population, and then we consider the product over I over k such populations. So, let us see how we handle it. The likelihood function that we consider here is, we have L, and then this is nothing but mu1 to mu2 to mu k, and then sigma, obviously conditioned on the observations. We are not rewriting it now. Now, what we have is usual, for the usual case what we would write is, this is twice pi, and instead of n by 2 we would write ni by 2, because the ith population has size ni, and then we would write the determinant of the variance covariance matrix, which is sigma, this raised to the power minus n by 2, no longer n by 2, I would write n I by 2, and then we have the exponent term, right. What was that? So, I have minus half, and then I have two subscripts for the observations now, right. Let us forget about the ith population for the time being. Let us consider the observations when I is fixed. So, this is sum over j from 1 to n I, and then I have the mean vector pertaining to this population. I being fixed is now, obviously these are vector observations. So, this is mu I, and then we have the usual variance covariance matrix, its inverse, and then we have Xij minus mu I, right. Now, what we have now is k such independent populations. So, as a final step, we consider the product of these over I going from 1 to k. So, that is the only difference. We are using two subscripts for the observations. We have a different mean vector in every population. So, it is mu I, and we consider the product over k such populations. Okay. So, we have to find, firstly say, let us concentrate on the denominator part where we do not have any restrictions. So, we have got to maximize this likelihood function to get the MLEs of these parameters. So, the usual principle, recall what you had done when you had sampling distribution from a single population. What we did was, initially we fixed sigma and then tried to obtain the MLE of mu. So, we do the same thing. So, by the usual technique, by the usual maximization technique, considering derivative. So, by the usual maximization technique, fix sigma, we have L mu 1 to mu k sigma maximized at when mu I hat is x I bar, and then this plugging these estimated values of mu i's, we have L mu 1 hat to L mu k hat, and then we have sigma, and this is now nothing but 2 pi raised to the power, well, we will do something here. Instead of this, since this is to the power, we write n p by 2, obviously n is nothing but summation n I from 1 to k, and similarly for this determinant term also we can write this is minus n by 2. So, n is the total sample size considering all the populations, and then we have this is nothing but minus half, and we have a double summation now here, the first one over I for the groups or populations, next one is for observations within that group. So, 1 to n I, and then we have x I j minus x I bar, because we are now putting the estimators of mu i's here. This is transpose, this sigma is for the variance covariance matrix, and then I have x I j minus x I bar. So, this will give us, this is being maxed at sigma hat, that is the only parameter involved now, sigma, and this is nothing but 1 by n, quite easily seen that this is 1 by n, a double summation, in fact this term in the exponent. So, we have x I j minus x I bar, x I j minus x I bar transpose, giving us a p by p matrix, square matrix, the first summation over A, the second over J. Okay, this is the situation when we have the unrestricted parameter space. For every mu I, we have mu I hat is xi bar, and the sigma hat is coming like a matrix like this. Now, if under H naught we have a simple situation like L mu sigma, because all the population means are now mu, and this is maxed at mu hat is the overall mean for a fixed sigma, and then and consequently the sigma hat under this restriction. So, let us write this sigma hat with an H naught here to distinguish from this estimator when it is estimated on in the unrestricted situation. So, this is nothing but we have 1 by n double summation. So, there is no question of xi bars. Now, we have the common x bar, and this gives me the estimator. Let us, though we can easily understand what are the what are these xi bar and x bar are, still we may write it here that xi bar is nothing but when we have the ith population fixed and sum is being considered over the observations in that fixed population. So, j is going from 1 to ni. This is obviously element by element wise, because this is not a scalar, but a vector valued observation now. And similarly, we have x bar is nothing but the weighted means of the different population means. So, this is going from 1 to k. So, we see that it is not really very different or at all difficult to handle the likelihood function when we have k population means. If they are independent, we can simply consider the product of each of the likelihood function for ith population and easily handle the maximum likelihood estimation case for the parameters involved in the unrestricted case as well as in the restricted case. Okay. Next, we consider the prime factor of this likelihood ratio test principle, the thing around what the whole principle revolves, that is the likelihood ratio criterion or the likelihood ratio test statistic. Okay. So, we go to the criterion. Once again we consider lambda. This is, well, we have seen that this is supremum of L under theta naught by supremum over L under theta, and we have actually seen what are the parameter estimates that are maximizing the likelihood function, and consequently we just put in these values here. So, we have now L mu hat sigma hat H naught according to our notation, and this is upon mu 1 hat up to mu k hat, and then our estimate of the variance covariance metric sigma hat. Now, if we do so, we can easily see that the whole thing can be simplified only to this factor involving the sigma hat matrices. We will simply get 1 by determinant of sigma hat H naught, this raised to the power n by 2, and similarly 1 by determinant of sigma hat also raised to the power n by 2. So, this is what lambda is coming to, and this is simply sigma hat determinant of that sigma H naught hat determinant of that raised to the power n by 2. So, what we do is we consider something which we denote by lambda star, and this is nothing but lambda raised to the power 2 by n. So, that we simply get this ratio here, which is determinant of sigma hat, and this is determinant of sigma hat under H naught. So, this is nothing but, well, this is nothing but determinant of MLE of sigma, and this is by determinant of MLE of sigma under H naught, and we very well know what are they, because we have just seen they can be derived also very easily, that this is nothing but 1 by n gets cancelled. We have two p by p square matrices. The first one is xij, xi bar, xij minus xi bar transpose sum over I and j, and in the denominator we have the matrix xij minus x bar, xij minus x bar transpose. Okay. So, this lambda star we would actually consider, it is very easy now to see that how to get the test statistic if we consider the likelihood ratio test principle. Since we have the data with us, it is not a problem to calculate, to get these matrices, the two matrices, and then to get their determinant also. These are now depending on the observations, they depended on the estimated parameters also, but those again in turn depended on the observations. So, obviously, this lambda or lambda star, whatever we talk of, is a test statistic. It's essentially got some numerical value if we have the observations, if we have the data at hand. So, this lambda star that we have here is called the Wilks lambda, and this is used for the test criterion, and we say the likelihood ratio test rejects H naught if the observed lambda star is small. Now, why is this? If you note what is the likelihood ratio that we are considering, it is supremum of L over the restricted parameter space, and then we take this over the supremum of L over the unrestricted parameter space. So, we are considering basically supremum over a subset. So, we can note one thing at least, that it has to be less than 1. This supremum in the numerator can never exceed the supremum in the denominator. So, this always has to lie within 0 and 1 essentially, because either we are considering joint PMF or joint PDF. So, positiveness is there, and this is also less than 1. And then when we see that this is close to 1, what is happening is that our assumption or the hypothesis that we have taken is pretty much close to the actual situation, actual parameter. So, then in that situation this ratio will be closer and closer to 1, and farther we are from the actual situation, this will go closer and closer towards 0. So, that is why the criterion is given in this way, that the rejection will be rejection of the null hypothesis over the alternative will be when the test statistic lambda star is small. Now, we can find the exact distribution. If the exact distribution of lambda star is attainable, then what will happen? We would try to find some value, say we would if the exact distribution of lambda star can be obtained, then we might as well find a value, say small lambda star, such that what is happening? We are considering the rejection region, that is lambda star is less than this value lambda star. Let us put a second subscript also alpha. So, this probability of rejection under the null hypothesis, which means that this should be equal to alpha if we have decided on the level of significance as alpha. So, thus then we can find this value such that probability is equal to alpha, so that an exact size alpha test is obtained. But unfortunately, in most of the situations it is very difficult to find the exact distribution of lambda star, and coupled it with it is the fact that in the likelihood ratio test principle, we can use a very strong result that for very large n, for large n under the null hypothesis, we have a function of this lambda star is converging in law or in distribution to the simple central chi-square distribution. So, we take help of the result. So, in the likelihood ratio test principle, let us use the acronym LR test principle. Note that, or we use that for large n under H naught, we have minus. So, I said it is a function of lambda, not exactly lambda. So, we have log of lambda is asymptotically converging. So, we are talking of convergence in distribution or law here, in law or distribution. To a central chi-square distribution. Consider if we want to have it in terms of lambda star, we will have minus twice of log lambda, which is nothing but minus twice then n by 2 log lambda star by its definition, and then we have this is simply minus n log lambda star. So, whether you calculate lambda or lambda star, it hardly matters, and this will follow a chi-square distribution. What about the degrees of freedom? Well, the degrees of freedom is dimension of the parameter space theta, but we are losing certain degrees of freedom, and from where is it coming? It is coming from the fact that we have put some restriction, which is basically our null hypothesis. So, we have to take out that degrees of freedom from the whole. So, it is basically the dimension of the unrestricted parameter space minus the dimension of the restricted parameter space. Let us see what is the degrees of freedom in this situation. So, we have degrees of freedom is equal to dimension of theta, in this case here minus dimension of theta naught. Now, recall how do this unrestricted parameter space looks like. We have k population means mu 1 to mu k, each of them is a p dimensional vector. So, that for the mean vector part, for the mean part we have p k number of parameters, and then we have the covariance matrix sigma. What is the number of parameters there? Recall that sigma being a covariance matrix is symmetric. So, we have p and then p minus 1 in this way to 1 till we go down. So, it is basically p into p plus 1 by 2 unknown parameters in the covariance matrix. What is happening in the restricted situation? There we have said that mu 1 to mu k are all equal and equal to a common mean vector mu, which is p dimensional. So, it has p unknown elements in it, and the sigma, the covariance matrix, since it remains the same, the number of unknown parameters pertaining to that also remains same, and we have p times p plus 1 by 2, and this is giving me the value p times k minus 1. So, we have asymptotically to come to a decision, we are going to use that asymptotically for large n, that is under H naught minus n times log lambda star follows a central chi-square distribution with degrees of freedom p times k minus 1. Let us recall n is the total sample size, that is sum of the sample sizes over each population. So, n is nothing but summation of n I, p is the data dimension and k is the number of groups or number of populations that we are handling. Okay. The test procedure next is the decision. As we have already said that it is we reject H naught, the null hypothesis if the observed value is small. So, what is happening here? We are considering minus of n log lambda. So, the test procedure is obviously reject H naught in favor of H A at level alpha if the observed value of minus n log lambda star or minus 2 log lambda, whatever you consider, is greater than chi square p k minus 1. This is the cutoff point. So, let us put some alpha here, where chi square alpha p k minus 1 is the upper alpha cutoff point from a central chi-square with degrees of freedom equal to p times k minus 1. So, roughly we will have a situation like you have a upper alpha point here, cutoff point here, chi-square alpha p k minus 1 df. So, this area is alpha. As an alternative to this, people sometimes use the Bartlett's test. Bartlett's test is just a change in the constant terms before this log lambda star or log lambda. Instead of minus n, we have a little different expression here. It is minus n minus 1, and then we have a minus p plus k by 2. A little longish constant term attached with the main statistic, and then we have this log lambda star, and this is also following. So, we say for large n under the null hypothesis, this also asymptotically follows the central chi-square with p k minus 1 degrees of freedom, and so the test criterion is same as this one, only thing is the statistic is going to be this. So, this Bartlett's test provides a better approximation in the sense faster convergence, in the sense of faster convergence to the central chi-square distribution. Right. Since it is an approximation, if we know, if we have something that gives a better approximation of faster convergence, and since this does not involve much of an extra labor from the usual likelihood ratio test, we might as well use the Bartlett's test. Now, there are a few alternative tests to this, but pretty much based on the same principle. We are going to discuss the basis of such alternative tests, and then going to just very briefly mention what those alternative tests are. Okay, these are as we see, this will depend on the eigenvalues of the matrices that we have obtained, that is sigma hat and sigma hat H under H naught. Okay. So, now we are considering the eigenvalue based tests. for which we once again recall what our Wilks lambda is. Lambda star is nothing but lambda raised to the power 2 by n, and which was nothing but the estimate of the variance covariance matrix in the unrestricted situation by the estimate in the restricted situation, and what we got was essentially the determinant of two matrices Xij minus Xi bar, and then we have Xij minus Xi bar transpose. So, this is over I and j, determinant of this matrix divided by the determinant of another matrix of the type Xij minus X bar, Xij minus X bar prime, right. So, this is what our Wilks lambda is, and now we give some special name to this. We call this matrix, which is coming in the numerator, that is a sigma hat matrix, as W, and the denominator, in the denominator we have the sigma hat under H naught, we give this the name B plus W. So, we have the ratio of determinant of W by determinant of B plus W, and then obviously my W is, let me write it again, it is the matrix Xij minus Xi bar, Xij minus Xi bar prime, and B is, or not B, but B plus W is whatever is given there, and from here I can see that if I consider B, it is nothing but, so let me write this once again. So, this is Xij minus X bar, Xij minus X bar prime, giving me B matrix as, what we have to do is actually take plus and minus of Xi bar in this expression B plus W and obtain my B matrix as Xij minus Xi bar, Xij minus Xi bar transpose, sorry, just a little correction here, this is Xi bar. So, we have Xi bar minus X bar, that is why we have the single summation. So, that is Xi bar minus Xi bar prime over I. Note this W matrix is nothing but the, if you think of the situation where you have the p equal to 1 case, that is you do not have vector valued but scalar valued random variable, then what is this? This is simply this W is summation Xij minus Xi bar, and we have a whole square over it because p is equal to 1 and we have a scalar value for that, right, and in that case it is the within sum of squares, if we recall. So, this in the multivariate analog, this is called the sum of squares, or the within sum of squares and cross product. This is the extra term we use in the multivariate case, cross product matrix, and B is nothing but the between sum of squares and cross product matrix, right. So, what is then lambda star, the Wilks lambda, the reciprocal of it? Well, it is nothing but determinant of B plus W by determinant of W, and let us do a little bit of manipulation here, that we consider, we try to take out this determinant W common from the numerator. So, what we do is we post multiply, say this by W inverse, and we have the identity here, so that we have W matrix being taken common in the numerator, and we have this here. So, since determinant of AB is determinant A times determinant B, we simply have this as BW inverse plus I, and we have determinant of W by determinant of W, which is now giving me the determinant of BW inverse plus I. I have a matrix here, no longer a ratio, I have a simple determinant. Now, W inverse exists because W after all gives the MLE of sigma. So, that is not the determinant of which is not 0, and inverse exists as a result of which. So, we have this is coming out, and then let us consider the spectral decomposition of this matrix. So, that we have P d lambda P prime, our usual spectral decomposition method. So, let us write the eigenvalues are now coming into the picture as soon as we talk about the spectral decomposition. So, these all being P dimensional square matrices, let lambda 1 to lambda P be the eigenvalues of the matrix B W inverse plus the identity matrix. Okay. So, if we have these the eigenvalues, then we can give a spectral decomposition of this matrix, and we can write that this is nothing but the Wilks lambda criterion reciprocal of it, which is nothing but determinant of BW inverse plus I. This is giving me a determinant of I plus P d lambda P prime, right. So, this P d lambda P prime is spectral decomposition of the matrix B omega inverse. So, that d lambda contains the eigenvalues. So, if that is the spectral decomposition of B omega W inverse, then these are the eigenvalues of BW inverse and not of BW inverse plus I, because we are keeping this I still separate and using PD P prime for this part only BW inverse. So, it is spectral decomposition of this matrix, and as a result these are eigenvalues of BW inverse, and P is the orthogonal matrix where columns are the corresponding orthonormal eigenvectors. Okay. So, this is again we can handle this by we consider determinant of I plus P d lambda P transpose, because we have P matrix as orthogonal. We can very easily take P common out of here, and we write d lambda here, and P transpose is getting outside from here, and then we have this as nothing but the determinant of 1 plus d lambda, and then it is determinant of P transpose, which is the identity matrix, which is equal to 1. So, this is basically, now we have a matrix I plus d lambda, both are diagonal matrices. Till now we had a diagonal matrix with lambda 1 to lambda P as the diagonal elements. Now, we have lambda I plus 1 as the diagonal elements, and we are considering its determinant a diagonal matrix. So, this is nothing but product of 1 plus lambda I from 1 to P. So, you see very easily, once we have these matrices obtained from the data, which is the matrix B and the matrix W, then we obtain the W inverse matrix. What we do is then consider a product of B and W inverse, and then calculate the eigenvalues of that matrix. So, we get P eigenvalues lambda 1 to lambda P, add 1 with each of them, consider the product, and that immediately gives me the value of the test statistic, that is the Wilks lambda. So, this is now my value of the lambda of the Wilks lambda, and I can form my test criteria based on this value. So, that is why it is called the eigenvalue based test, because all the whole thing boils down to eigenvalues of the matrix B W inverse. Okay. So, let us list down the few tests which consider these the statistics in this form. So, our first one is, obviously if we talk about the likelihood ratio test, the test criteria is rejects H naught in favor of the alternative Consider what happened in the beginning. We had talked of lambda star if lambda star is small. Now we are considering reciprocal of lambda star. So, the test is going to reject H naught when this reciprocal is large. Now we have the reciprocal in terms of the eigenvalues. So, we say it rejects H naught if the test statistic, that is reciprocal of lambda star or the product of 1 plus lambda I from 1 to p is large, because this is equal to not the statistic, but its reciprocal, that likelihood criterion, but its reciprocal. Okay. So, the alternative tests are, this is the basic one, and then there are some other tests also using eigenvalues, but in a slightly different form. The criteria basically is a slightly different form. So, this, the first one says that you reject H naught if sum of lambda I, which is nothing but the trace of the BW inverse matrix I from 1 to k, sorry, it is not I from 1 to k, but I from 1 to p, that is a dimension of the data, is large, because this is the trace, and this is due to Lolly and Hotelling. This is called the Lolly and Hotelling trace test. The next one is reject H naught if maximum of these is large. Makes sense also if going by this principle, and this is called Roy's maximum root test. Root means here the characteristic root, which is another name for eigenvalue. Something more, we have reject H naught if summation lambda I over 1 plus lambda I, this is large, and this is by Bartlett et al. So, these are the few tests where we can use the eigenvalues of the estimated variance covariance matrix in the unrestricted situation, giving us the matrix W, and the estimated variance covariance matrix in the restricted situation, giving us the matrix B. Again, what we calculate is the product of BW inverse. We get the eigenvalues of these of this matrix, and just consider different forms, different functions of these eigenvalues to reach to different testing criterion. Okay. Now, we extend this discussion on the equality of k population means when the observations are coming from multivariate normal distribution, for the purpose of moving to our next topic, which is MANOVA, that is the multivariate analog of ANOVA or analysis of variance. Okay. If you recall what we do in analysis of variance, we have the data and we try to look at the data and try to look into the variability of the data and to assign them to different sources of variation. So, here also the same thing is being done, but the only difference is instead of the random variable, we have a vector valued random vectors now. The data that we have at hand, they are multidimensional data, and we try to generalize the ANOVA to the multivariate situation. So, now our next topic is multivariate analysis of variance. In short, MANOVA, and we consider as in the usual ANOVA context, what we do here is in the simplest situation we consider a model. So, we have Xij, and then we have its mean effects, say mu I, and an error term, that is Eij. The difference here is these are all vectors, multidimensional data are being considered. So, these are all vectors, and we have expectation of Xij. Well, mu I is the mean effect mu I, right. This is the mean effect. So, giving us this gives expectation of the error term. This is obviously equal to 0. Now, additionally, we assume the equality of variances, we assume uncorrelatedness, and we also assume that the data, the variables are coming from multivariate normal population. So, we might as well say that actually we have these error terms Eij, they are IID, uncorrelated, and normality, giving them independence, and we have them coming from the multivariate normal distribution NP with mean 0 and variance covariance matrix sigma. So, let us write the, we also do a further manipulation, we would say to obtain upon the treatment effect, what we do is we break this mean effect and we try to obtain a grand mean effect out of it. So, what we do is we say that mu I is the mean effect is equal to the grand mean effect or the overall effect, and obviously then we have to write the rest of it in this way. All of these are vectors here, where this mu is the overall or grand mean effect, right. So, for this second part we use a notation for the treatment effect. That is what we do in ANOVA, that is this being the treatment effect tau I, now a vector again here. And so, the one way ANOVA, let us now write the one way MANOVA model explicitly. You have the data Xij, right, the jth observation from the ith group, that is equal to the overall effect mu plus the treatment effect tau I and the error Eij, where Eij, this is important, our assumption, these are IID normal 0 sigma. Let us also give brief definition of a brief introduction of this also. So, we have mu is the overall or the grand mean effect, overall effect, tau I is the ith treatment effect, with, note that what is tau I, it is nothing but mu I minus mu. So, we have a restriction here, we have a constraint that sum of tau I from 1 to k, this is equal to 0. Here we said that we have k groups, so I goes from 1 to k, same thing like saying it has k populations. So, I from 1 to k, and number of observations in each group, that need not be constant. So, we have j going from 1 to ni, and Eij is the error, jth error for the ith group. Just like we have Xij, that is the jth observation from the ith group. Now, we are trying to look at the variability of the observations and trying to assign them to the different sources of variation. So, for this purpose, the hypothesis that we are testing is nothing but the hypothesis we just looked at now, and we are interested in ANOVA or in MANOVA, we are interested in testing that same thing that is happening. We have, instead of writing the null hypothesis in terms of mu I, it is equivalent to write it in terms of the treatment effects. So, now that we write this is all the tau i's are equal, tau 1 to tau k, against the alternative there exists at least one inequality. So, this is the setup of the one-way ANOVA model, where we see that we are going to use the testing procedure, whatever we have learned just now, how to test, how to compare between the k population means when the random samples are coming from the multivariate normal distribution. Here we have this assumption in place, and the observations are also coming from multivariate normal distribution, and then we are using this equality of the k treatment effects, which is equivalent to saying that we are basically testing the equality of the mean effects mu 1 to mu k. We simply split a data vector, we split an observation vector as we have xij. Looking at it, we bring down the overall mean, sample mean, and then the group means xi bar minus x bar, and then obviously the rest of it, which is xij minus xi bar. Now, this is giving me the overall sample mean. Let us write these. So, where the overall sample mean is very comfortably giving me an estimate of the grand mean, overall sample mean, and this is nothing but mu hat, and we have xi bar, the group means xi bar. This is estimated treatment effect. We are calling this as not the mean effect now, because we have separated out an overall effect, and we call this as strictly the treatment effect, the ith treatment effect, estimated ith treatment effect, and that is tau I hat, and the rest of it is nothing but the residual. So, that has got the notation residual, which is Eij hat. So, we are going to look at how we obtain the treatment sum of squares and the residual sum of squares and the total sum of squares, and we follow it up with the one-way MANOVA table, and also look at the test statistic for the hypothesis that we have stated.